Let's do a review of the May 2019 version 2 of paper 1. All right. So, number 1. A student measures the radius r of a circular plate to determine its area. The absolute uncertainty in r is delta r. Delta r is absolute uncertainty. It's important that you remember the difference between absolute uncertainty and fractional uncertainty. Fractional uncertainty is like percent error. Absolute uncertainty is how much it's off. So if we've got something that's like, 10 centimeters plus or minus 0.01 centimeters, 0.01 centimeters is the absolute uncertainty. That's how far off we might be, how far above or below. The fractional uncertainty would be 0.01 divided by 10. Right, that's the percent of our uncertainty, just to make sure we're clear on that. So now, okay, student measures, okay, so the area is pi r squared. Now, when we square something, the way we deal with percent error, or rather, the way we deal with error, is we just take that power and multiply that by the fractional uncertainty. In this case, the fractional uncertainty is delta. Well, they use a capital R, so I'll use a capital R now. It should have been a capital R. Delta R over R, and then we multiply it by 2 because we're squaring it. This is the same thing as if we had R times R. In that case, we would do delta R over R plus delta R over R. When we do fractional uncertainties, rather when we do uncertainties for things that are multiplied or divided, we add the fractional uncertainties. We also add them when we divide the things. If it was R divided by R, the fractional uncertainty would still be delta R over R plus delta R over R. Well, delta R over R plus delta R over R, isn't that just 2 times delta R over R? Same thing. So that's why you bring that 2 down. And then, of course, the pi you don't care about. There's no uncertainty in pi. It's a number. So, A. What is the unit of electrical potential difference expressed in fundamental SI units? So there's usually one of these questions where they ask you to express some derived unit in terms of SI fundamental units. So I would just go through, if I were you, go through all of the units that we use in this class and make sure you understand how to get them. Now, do I have that memorized? Absolutely not. In fact, even I start with V equals IR, but then that kind of gets into the weeds. And that's not the definition of a volt. A volt is actually defined as the potential difference that will produce 1 watt of power through a wire that has 1 amp of current going through it. So it's defined based on power. So power equals current times voltage, right? P equals IV. So you just isolate the V. You get V is equal to P over I. And that's where this comes from. So 1 volt is defined as 1 watt and 1 amp for those two values. So I did 1 watt divided by 1 amp. Well, a watt is joules per second, and then amps is amps. Amps isn't going to change. Amperes are a SI fundamental unit. The coulomb is not a fundamental unit. The ampere is the fundamental unit. A coulomb is defined as the charge that passes through one. The charge that you get when you have 1 amp flow for 1 second. That is the definition of a coulomb. So it's not the other way around, where you do 1 amp is defined as 1 coulomb per 1 second, which seems silly, I know, but that's how it's defined. Okay, now a joule. Well, joule is the unit for work, and work is force times distance. Right, so we have newtons times meters for force and distance. Well, a newton is also not an SI derived unit. Newton, well, that's F equals MA, right? Net force equals mass times acceleration. Well, mass is kilograms, hence I forgot the G there, hence the kilograms. And then acceleration's meters, so there's another M there, that's why, and there was already an M there, that's why it becomes M squared. Per second squared, and now there's already an S there. If I divide by seconds squared, I get seconds to the 3rd power, and then my amps are still just sitting there. That's the one that matches. The graph shows variation of velocity of a body with time along a straight line. What is correct for this graph? Okay, well, this is a velocity graph, so the area represents displacement, and the slope represents area. The maximum acceleration is at P? No, the maximum acceleration would be somewhere like there, it looks like to me. Or actually Q looks like it would also be potentially a maximum acceleration, where the slope is steepest. Not most positive, but steepest. It could be steeper in the negative direction than the positive direction. We just care about steepness. So no. The average acceleration of the body is given by the area? No, acceleration is given by the slope. And in this case, the average acceleration would be given by the change in slope from there to there. And this, in this case, overall, the change in slope from there to there is 0. The maximum displacement is at Q? No. Well, maximum displacement actually looks like it's probably, actually it would be here. Maximum displacement would be there. Total displacement of the body is given by the area enclosed by the graph. Yeah, there we go. The area of a velocity graph moves you up to the position graph. The slope of the velocity graph moves you down a level to the acceleration graph. If you know calculus, that's even easier. All right, two forces of magnitude 12 newtons and 24 newtons act on the same point. What force cannot be the resultant? So the maximum possible resultant force is if they're parallel to each other. We've got a 12 and then a 24. We end up with a 36 Newton force. The minimum possible force is we have them anti-parallel. We've got a 12 and then a 24, in which case we would end up with a negative 12. And you're talking about, not talking about magnitudes, but we could get a magnitude of positive 12 if I do the 24 that way and then go back 12. Then the resultant would be positive 12. But hey, we cannot get down to 10 though, can we? There's no way we can get 10 newtons for the resultant force. It's smaller than the minimum force, so it's not possible. And of course, if there are various angles to each other, you can have any value between 36 and 12, or rather between 12 and 36 for the magnitude of that resultant force. An object has a weight of that's 610 newtons. What is the change in gravitational potential energy of the object when we move through 8 meters vertically? So all these are the same answer to different sig figs. So the question is, how many sig figs? The answer is 2 sig figs. This says 3 sig figs, but that's 2 sig figs. You go with the fewest sig figs, so the answer is B. That's 2 sig figs. If you want to do the problem, you would say, okay, gravitational potential energy, or you can say U for your potential energy. Either one, I tend to default to that one. They use that one usually. You go to mg delta h, and then you can plug and chug and solve, but you don't even need to do that because these are all the same answer. A boat with an output engine power of 15 kilowatts moves through the water at a speed of 10 meters per second. What is the resistive force acting on the boat? All right, well, power, how do you compare power and force, or how do you relate power and force? Well, you do that with P equals FV. So then force is equal to power divided by velocity. We know the power, we know the velocity. That's 15 kilowatts. Kilowatts, so it's times 10 to the 3 divided by 10. Well, it would be 15 times 10 to the 2, which would be 1,500. So 1.5 kilonewtons. Remember, no calculator on this part. An astronaut's moving at a constant velocity in the absence of a gravitational field when he throws a tool away from him. What is the effect of throwing the tool on the total kinetic energy of the astronaut and the tool total momentum of the astronaut and the tool? Well, kinetic energy is going to increase. At the beginning, they have 0 kinetic energy because they have 0 motion. And then at the end, there is motion, both for the tool and the astronaut. Those do not cancel out because kinetic energy is never negative. So the kinetic energy must increase. Therefore, these two immediately go away. Now, what happens to total momentum? Well, momentum is conserved because there are no net external forces acting on the tool and the astronaut. The total momentum is still 0. Right, they start with 0 momentum. One of them, the astronaut, let's say, has a momentum that way. The tool has momentum that way. They cancel each other. They balance each other out. They don't cancel each other out, but they balance each other out. So you still have 0 momentum. Again, that does not work with kinetic energy because kinetic energy is not a vector and it's never negative. Moving on. Maybe I should see if I can go a little bit faster. A table tennis ball, mass 3 grams, is fired with a speed of 10 meters per second from a stationary gun. Okay, what are the recoil speed? Okay, so total momentum of this system. Well, immediately we can say the total momentum of the system has to be 0, so we can eliminate B and D. Then we need to actually know what is the speed of the toy gun. Well, if they start out at rest, they've got to have the same momentum before and after, or as each other after the collision, just in opposite directions. So dealing in terms of magnitude, their momenta will be the same. So big M for mass of the gun, VG for mass of the gun, little m for mass of the ball, and VB for velocity of the ball. They tell us the velocity of the ball, they tell us the mass of the ball, they tell us the mass of the gun. So we just solve for the velocity of the gun, dividing the big M over, plug in our numbers, and now, again, no calculator on this part, but 3 divided by 6 is a half. So a half of 0.003 is 0.0005. But then this is a decimal, right? So you're going to move this decimal that way 1, so you get 0.005. And then there's the fact that you're multiplying by 10, so you move it over one more spot, 0.05. A. Number 9, so we have a block sliding down a ramp at a constant velocity. The constant velocity is the important part here. That tells us that the forces have to be balanced. So you look at these and figure out which ones are balanced. All right, so in this case, well, they can't be, so the way we break this down is usually we break it down by bringing gravity down. Hey, these two need to be balanced. This is bigger than gravity, so it can't possibly be an answer. This one, well, this one's way too small compared to gravity, as is that one, so that's not the answer. In this case, well, the friction force is too big, and I think the normal force is probably too big. If we break down that gravity, it would be something like that. Yeah, those are both too big. Now here, if we break this down and that down, those look about the same size, those look about the same size. So it's D. We just are looking for the one that has a balanced force diagram because we have a constant velocity. Number 10, a substance changes from the solid phase to the gas phase without becoming liquid and without a change in temperature. What is true about the internal energy of the substance and the total intermolecular potential energy of the substance? Okay, well, for a gas, we typically take it to have no intermolecular potential energy. Now, for a solid, it's actually got negative intermolecular potential energy. So you go from a negative intermolecular potential energy to 0, that would be an increase. So A and B are gone. And now what happens to the internal energy? Well, the internal energy of the substance is going to increase because it didn't increase in temperature. Therefore, the kinetic energy did not increase. However, the internal energy of a substance is the sum of kinetic energy plus intermolecular potential energy. Or again, you can always use a capital U. So if that increased, then total internal energy must have increased. If that remained the same. Number 11, the temperature of a fixed mass of an ideal gas changes from 200 to 400. What is the mean kinetic energy? Okay, so this one's kind of tricky. You got to remember that that's Celsius. You need to do things in Kelvin. And you have an equation in your data booklet in case you don't remember this. Right there, average kinetic energy, and this is for topic 3, is equal to 3/2 kb times T. So that means they use E sub k. I'm going to use a capital K for kinetic energy. That means K is proportional to T. Average kinetic energy is proportional to T. So you may immediately think there's going to be 1/2, right? You can maybe even see that before I realized how stupid I was, I circled A. But no, this has to be done in Kelvin. So you need to convert these to Kelvin by adding 273 to each of them. And then you get this, and now obviously this is more than 1/2, but it's less than 1, less than 2. Or less than 1.4, less than 2. It's less than 1, so these are gone. It's more than 1/2, so that's gone. So it must be 0.7. Let's just verify that. 473 divided by 673. Oh my goodness. This is in scientific mode, so let's change that. That looks kind of weird, I know. Let's try that again. Oh, 0.7. Wow, good. So you don't actually have to do the calculation, right? I use a calculator. You're not allowed to use a calculator in this part. You don't actually have to do the calculation. In this case, it's obvious that that's the only possible answer. Although I'm sure you could do it with long division. That said, generally, if you're doing long division in this section, you're probably doing something wrong, because that shouldn't generally be necessary. A container holds 20 grams of argon 40 and 40 grams of neon 20. What is the number of atoms of argon 40 divided by the number of atoms of neon 20? So the ratio of the number of atoms. Well, argon 40 has a molar mass of 40 grams, and you have 20 grams, and that means you have half of a mole. Neon 20 has a molar mass of 20 grams. You got 40 grams of it. That means you have 2 moles. What's a half divided by 2? It's a quarter. Okay, the graph shows a variation of the displacement of a wave with distance along the wave. The wave speed is 0.5 meter per second. Okay, what is the period of the wave? Well, this graph will allow us to find the wavelength. They tell us the velocity. We can find the wavelength. I would think to use this equation. The velocity of a wave is equal to the wavelength times the frequency. Now, of course, frequency is the inverse of period. It's 1 over period. So I just plug that in for frequency. So I get that velocity is equal to the wavelength divided by the period. Solve for the period, multiply that up, divide that down. Period is wavelength over velocity. The wavelength, if I look at this, from nya to nya is 1 full cycle. That's 1.5 meters. So I do 1.5 meters. Divided by the velocity is 0.5 meter per second. 1.5 divided by 1/2 is the same thing as 1.5 times 2. Right, because it's 1.5 divided by 1/2. That's a double denominator comes on top. So it becomes 1.5 times 2 divided by 1. That's 3 seconds. The period. Number 14. Object P moves vertically. Let's get rid of this calculator. Object P moves vertically, so this moves up and down in simple harmonic motion, and this is executing uniform circular motion. Remember that simple harmonic motion is uniform circular motion just viewed from the side. So these are really the same type of motion, and they're just 180 degrees out of phase. They're exactly out of phase. So what is the interval between successive times when the acceleration of P is equal and opposite to the acceleration of Q? Well, it'll be equal and opposite there at the, most obviously, at the ends. That happens every half of a period. So T over 2. T over 4 would be coming to here, the equilibrium position for this one. And from this perspective, looking that way, the equilibrium position for this one as well. But in that case, they both have 0 acceleration from the perspective of someone over here looking to the side. Now, realistically, this one actually always has the same acceleration that way. Right? That's what makes this problem work. If this was also undergoing simple harmonic motion up and down, they would be way more frequently than T over 2. In fact, this would be the only time when that wasn't true. But because this always has the same acceleration toward the center, this one has varying accelerations in that direction and that direction. So these 2 points are the only places when this one that's undergoing uniform circular motion has vertical accelerations, like this one does. So those are the only 2 possible times when you could have the same but opposite accelerations. 2 different ways to look at that one. The second way is probably the better way. Okay, we have unpolarized light that's incident on this first polarizer, and then we've got second polarizer, and we twist around the second polarizer. Okay, so when the second polarizer is horizontal, right, then this one is polarizing light, so you only have vertically polarized light coming through. This one's going to be polarizing, so you only let horizontally polarized light through. So you're going to get nothing at 180 degrees. I'm sorry, at 90 degrees. Now, you'll never get negative intensity, so D immediately goes away. Now, at 180 degrees, you just flip this one. Well, there's no difference between polarizing things that way and that way. They're the same thing. So at 180 degrees, you should get maximum intensity. And the only one that does that is B. Now for A, we see it's 0 and 0. That doesn't make any sense. And then this one at 90 degrees, halfway from 0 to 180, we've got that 0 intensity, as we should when the polarizers are exactly 90 degrees apart. Number 16, this one's pretty tough. Down here, I was working on a example to demonstrate why this happens. So we've got glass to air. We send light through the glass. It hits the air, and we're at the critical angle. So it does not actually come out. It just skitters across the surface there. This only works when you go from a high index of refraction to a low index of refraction, not the other way around. So now what happens if we put some liquid on here that's got a lower index of refraction than the glass, but a higher index of refraction than air? Well, it's not actually going to change what happens. Here's why. So I did this example of, let's suppose that we have the index of refraction of air is 1, of the glass is 1.5, and of the liquids, let's say 1.3. So I figured out that the critical angle from glass to air is 60 degrees. So then if we have this light coming in at 60 degrees to the liquid, we just do Snell's law here. N1 sine theta naught, I called that theta naught, that's 60. And then N3, I called this 3, that 1, that 2, this 3. And I found that the angle here would be 87.8 degrees. And I didn't write this down, I just did it in my calculator. But if we now were to figure out, forget about that, if we now were to figure out the angle that this would, or the critical angle from here to there, and actually that's what I was doing there, so I should not have gotten rid of that. So theta critical from N3 to N1 would be the arc sine of, so when we have a critical angle, what we're going to have is that this angle, the second angle, is going to be 90 degrees. That's 90 degrees there. So sine of 90 degrees is 1. So this goes away. And we just have the critical angle happens when the sine of that critical angle is equal to the index of refraction of the object with the lower index of refraction divided by the index of refraction of the object with the higher index of refraction. And so let's do that. So we're going from the liquid to the glass. So it's going to be 1 over 1.3. Now, this is not something you could test out really well on this portion of the exam. So you can't really use the numbers like this unless you're really good with your trigonometry and estimating your values. But we would do what we would do the arc sine. Are we in degrees mode? Yes. We will do the arc sine of 1 divided by 1.3. And we get 69 degrees. This is at an angle that's greater than 69 degrees. So we are just going to have the same sort of deal going on there. Just want to see something real quick about this calculator. There we go. That makes more sense. Okay. See, this did the inverse sine of 1 and then divide by 1.3. This is proper. So 50 degrees, even more. So we're still going to have that same sort of deal happen. Because again, we're beyond the critical angle going from here to there. Number 17. A student blows across the top of a cylinder that contains water. Okay, so now the speed is going to be the same. And we're always going to have a node right there because we cannot have air molecules. So air molecules would want to vibrate that way and that way. Well, here they can't do that. So at the surface of the water, we're going to have a node always. What's the nature of displacement in the air at the water? So immediately we can eliminate A and B. So now the question is, what's going to happen to the frequency? Okay, well, for the first harmonic, right, did they say the first? Yeah, first harmonic, The first harmonic is going to be, in this case, an antinode node that is going to be a quarter of a wavelength. This distance is a quarter of a wavelength. That distance, shorter distance, is also a quarter of a wavelength. But the speed of sound is a constant. And the speed of sound is, like for all waves, wavelength times frequency. Well, the wavelength in this cylinder with more liquid has gotten smaller. Therefore, the frequency must increase, d. A particle with a charge Ne, where E is the elementary charge and it's just some number times E, N is almost always, in this context, an integer, is accelerated through a potential difference V. What is the magnitude of the work done on the particle? Well, work is equal to charge times voltage, or energy is equal to charge times voltage. I think in your data booklet it's given as V is equal to work over Q. Let's verify that. Wrong packets. Yep, voltage is equal to work over charge. So it's work done to separate the charges divided by how much charge you separated. Okay, well, the charge is N times E, and the voltage is V. So NeV. Easy peasy. B. Number 19. The resistance of component X decreases when you hit it with light. So the resistance of that decreases when you hit it with light. Okay. X is connected in series with an ammeter and a voltmeter. They're both perfect ammeters and voltmeters. So that means a perfect ammeter has zero resistance. A perfect voltmeter has infinite resistance. In reality, real ammeters have very, very, very low resistance because they're put in series in a circuit, and you don't want the resistance of this to reduce the overall current. So that's why ammeters want to have very low resistance. Voltmeters, you want to have very high resistance because you're putting it in parallel. Voltmeters always go in parallel with the component you're measuring. And you don't want to have too much of the current come around through the voltmeter and therefore, again, mess with the thing it's trying to measure. So you want a very high resistance here. So a negligible amount of current goes through there. Very low resistance here. So you have a negligible effect on the current in the circuit from this. So what does he change in the reading in the ammeter and the voltmeter when light hits this? Well, when light hits this, this resistance will decrease. This resistance decreases, the overall resistance of the circuit decreases. Now we know V equals IR, Ohm's law. So I is equal to V over R. V has stayed the same, resistance has decreased, therefore current must have increased, the reading in the ammeter will increase. C and D are gone. Now what about the voltmeter? Well, for the voltmeter, we're going to have more current flowing through. That means this one is going to have a bigger voltage drop, because again, V equals IR. Same resistance for this, but a bigger current going through it. So the voltage is going to, for this, a voltage drop over this is going to increase. Well, the voltage drop for the sum of these two has to be equal to the battery. That has not changed. This voltage drop has increased. Therefore, there's less voltage available for component X. Therefore, the voltmeter reading must decrease because its voltage drop will decrease. A. Three resistors of resistance 1, 6, and 6 are connected as shown. The voltmeter is ideal and the cell has 12 volts with no internal resistance. Okay, what's the reading in the voltmeter? That voltmeter. Okay, so what I did is I found, well, how much current will be going through the entire system so I could figure out how much voltage drop we'll have here. And the voltage reading in this ammeter is going to be 12 minus whatever the voltage drop through that resistor is. So I need to have the current through that resistor to know the voltage drop. Well, these two are in parallel to 1 over R1 plus 1 over R2 to the power negative 1. When they're both the same, it's very easy, but I'll still do it manually. 1 over 6 plus 1 over 6 to the power negative 1. That's equal to 2 over 6 to the power of negative 1, which is equal to 6 over 2, which is equal to 3. So this has a resistance of 3 ohms. Put that in in series, this parallel complex in series with that 1, and you get a total resistance of 4, because you just add up in series. So 3 plus 1 is 4, and then current through this wire here, not through each of these, but through this main wire, is going to be V over R. So you get 12 divided by 4 is 3 amps. Now, specifically, you get a 1.5 amps going that way, 1.5 amps going that way, because these are the same resistance. If this was a bigger resistance than this, you'd get more current going this way than that way. So then I know that the current going through here is 3 amps. Well, V equals IR. Current is 3 amps. Resistance is 1 ohm. This is going to consume 3 volts. So positive 12 volts plus negative 3 volts consumed is 9 volts. Okay, horizontal wire. Okay, we have a wire going through there. We have a length of the wire and the strength of the magnetic field. Okay, now the magnetic field lines go from north to south. Remember that. Positive charges, electric field lines go from positive to negative charges for electric fields. For magnetic fields, they go from north to south. North is kind of like positive. Okay, so what's the magnitude and direction of the current in the wire? Well, if magnetic field goes that way, to figure out the direction of the force in the wire, I do, the direction of force is going to be QV cross B. Now, this is using a cross product. In your data booklet, I think you have this equation, but just V, so that's a direction of positive charge flow, that's the direction of the current, and you put your fingers in that direction, cross B, so cross your fingers, or I like to then bend my fingers in the direction of the magnetic field, which is to the right, and then your thumb points in the direction of the force. So the force must be downward. And they told us the force is downward, so it's good. Now, had I tried this way, I would have gotten the upward force. And they tell us the force is downward. So I knew my thumb was supposed to end up going downward. So that means I know the current's from Q to P. So that immediately eliminates D and A. Now I need to figure out the actual current going through there. Well, the force acting on a wire of some length L in a magnetic field of some magnitude B with a current of I is equal to Bill. It's really Bill with a trig function, but in this case, everything's perpendicular. It's sine of theta, but sine of 90 is 1, so we don't need to account for that. So for I, you just divide the B and the L over. The force they told us is 60 millinewtons. That's millis times 10 to the negative 3, 1,000th. B, they tell us, is 40 millitesla. So that's 40 times 10 to the negative 3. And then the length is a quarter of a meter. Well, the times 10 to the negative 3's cancel out. I cancel out that 0 and that 0. And then, 4 times a quarter is 1, right? Or you can think of this as 1 over 4 and bring that double denominator up, which is what I did there. The 4's cancel out, you get 6. So 6B. Number 22. A particle of that mass moves in a horizontal circle of that diameter with an angular velocity of 3 pi radians per second. What is the magnitude and direction of the force responsible for this motion? So angular velocity is just a way to describe the velocities or velocity with respect to an angle, right? So if I go like that, I've swept out a certain angle in a certain amount of time. That angle's in radians, and the time it takes me to do that is in seconds. So that's omega there, is the angular velocity. Now, in your data booklet, you're given that V equals omega times R. Now, we also know that centripetal force, because it's going in a circle, is equal to mv squared over r. So if I plug in omega r for V, I get m omega squared, and then I would get an r squared, but I have an r in the denominator, so the r squared at the top cancels out partially with the r down there, and I'm left with just a single r. So I have m omega squared r. Then I plug in my numbers. 0.02 for the mass. Now, omega is 3 pi, so it becomes 9 pi squared. And then r, this is tricky, it almost got me. Diameter is 1 meter, so the radius is 1/2 of a meter. So then you do 2 times 9 is 18, but you have to move the decimal place 2 spots over because it's 2 spots over, so 0.18. And then divided by 2 is 0.09 pi squared. So it's going to be one of those two. And then realistically, you probably did this part first. The direction of force for something going in a circle is always toward the center, so C and A are immediately gone. That leaves the answer of D. Number 23. Which graph shows the relationship between gravitational force F between 2-point masses and their separation R? Now, you probably were immediately thinking, it should be like that, right? Yes. If we have got force in R. Ooh, that means that one's not right. So these are linearized graphs. Now we know force of gravity is equal to gmm over r squared. But what if I separate out the 1 over r squared? Because notice here they've got 1 over r squared on the x-axis. Hey, what if force of gravity is my y, as it is in all these cases, and then 1 over r squared is my x, and then my slope would just be big G, big M times little m. That would be, this m means slope, that m means little mass. So this is like y-intercept form, except the plus b is 0. So D, right? Because this would imply that the force of gravity is equal to G, big M, little m over r. No, that's not true. Gravitational potential energy is negative G, big M, little m over r. Yeah. In this case, this would imply we end up with repulsive gravity. That doesn't make any sense. It would mean it changes sign. That doesn't happen. No. So this is the way you'd want to go. Okay, a radioactive nuclide with atomic number Z undergoes a process of beta plus decay. Okay, so that means we're going from a proton to a neutron. And when we go from a neutron to a proton, we emit an electron, because neutrons have slightly more mass than protons. But when we go from a proton to a neutron, we do the opposite. We emit an anti-electron, a positron or a beta plus particle. The atomic number of the nuclide produced, what is the atomic number of nuclide produced, and what is another particle emitted? Well, if we're emitting a beta plus, we emit a anti-electron, we emit a regular electron neutrino. So it's always the opposite, because you need to keep your baryon numbers and specifically in this case, actually, your lepton number has to be conserved. And so this has a lepton number of -1, so you emit a regular matter neutrino, which has a lepton number of +1, so that you have 0 lepton number on the right side of the equation. And that way you conserve lepton number. So this would be plus E plus, or you can write beta plus. I prefer to write E plus your electron neutrino. Lepton number 0, lepton number 0, lepton number -1, lepton number +1. Well, 0 is equal to 0 minus 1 plus 1. 0 does, in fact, equal 0. So lepton number is conserved. That's why these have to be opposite. For the other decay, if we go from a neutron to a proton, then that's going to be plus a electron and then plus an anti-electron neutrino. So again, we can conserve lepton number. This would be 1, and this one would be -1 in that case. So if we emit a positron, we have a regular neutrino that immediately gets rid of D and C, and then we're going down an atomic number, because atomic number is number of protons. We've converted proton to a neutron, so we've done Z minus 1, right? Z being the atomic number, we subtracted 1 from it, therefore A. 25. The positions of stable nuclei are plotted by neutron number and proton number. Neutron and proton number. It's different than proton number and overall nucleon number, right? Or mass number. Very different. Or different than neutron number and mass number. Neutrons to protons. Okay, which graph shows the line of stable nuclides and the shaded region where unstable nuclei emit beta minus particles? Okay, so that means we're going from a neutron to a proton. We're decreasing the number of neutrons, increasing the number of protons. Now, that would be, well, if we look at these, we want to be in a region where the ratio of neutrons to protons is higher and then it gets lower. So, for example, if we are, this is the right answer. So if we are in this region here to the left of the line, we turn one of these neutrons into a proton. We're going to move to the left, to the right and down. So we would move like there. Oh, that would bring us onto this line that we want to be on. Moving to the left, to the right and down could also be true here, but this is just not something, we don't really see this. We generally see that we get things that have more neutrons than protons. This is not really a thing, getting more protons and neutrons. For large nuclei, we tend to see more neutrons than protons. That's just not the relationship there. And the reason for that is balancing out the strong force and the electromagnetic force. That's why we get more neutrons and protons for large nuclei. Number 26, 3 conservation laws in nuclear reactions are charge, baryon number, lepton number, the reaction that is proposed. Which conservation laws are violated. Okay, so that's a Q. I started writing a B, but then I realized it was charge first. So that's a Q. Zero charge, negative charge, positive charge, zero charge. So charge is not violated. So that immediately eliminates B and A. Okay. Oh, and it eliminates D. My goodness. So immediately we know the answer is C. Wow. But let's verify that. So baryon number. It's a neutron, so it's got a baryon number 1. This, I know this is a pion. It's got a 2 quarks. One is an anti-quark. One is a regular quark. Those cancel out their baryon number, so we have baryon number 0 here. This isn't a baryon, so it's baryon number 0. This is not a baryon, so the baryon number is 0. So baryon number is not conserved. Okay, good. So 2 is violated. That's good. Lepton number. Not a lepton, lepton number 0. Not a lepton, lepton number 0. That is a positron, so it's got a lepton number of -1. It's an antiparticle. This is also an antiparticle, I know, because there's a line on top. That's a lepton number of -1. 0 is not equal to, this is where the equal sign should be, 0 is not equal to -2. Therefore, lepton number is also not conserved. Good. Number 27. Which Feynman diagram shows the emission of a photon by a charged antiparticle? Okay, so they have time flowing to the side. Now, in antiparticle, we do the arrow going backwards in time. This arrow is going forward in time. No. This arrow is going forward in time. No. Also, this arrow would be a particle interacting with another particle. So, no. It's not to create a new particle. No, we have a particle that emits something. So, no, that's another reason that one doesn't work. And now we're between these two. They're both antiparticles. Okay, but hey, this one is the antiparticle moving that way in time. Again, antiparticles, we put the arrow backwards to indicate they're antiparticles. And it then emits a photon and produces another charged antiparticle. And so we know it's an antiparticle because, again, the arrow is going the wrong way in time. So here they're both going the wrong way in time, but this antiparticle interacts with a photon, and you get another antiparticle, or maybe the same antiparticle. This is not what we're going for. We're going for it emits a photon. All right, a neutron collides head-on with a stationary atom. Okay, so this is about moderators. What are these changes? So there's also a change in the probability that this neutron can cause nuclear fission. Okay, so the change in kinetic energy of a neutron when it hits a moderator, well, the entire point of the moderator, it hits a moderator, it must lose kinetic energy. So that immediately eliminates A and C. Now, the purpose of the moderator is to reduce the kinetic energy of the neutron, so they're more likely to be captured by the uranium nuclei in the nuclear fuel. So it's going to increase the probability of causing a nuclear fission. That's the whole point. So B. 3 methods of production of electrical energy are wind, photovoltaic, fossil fuel. Which methods use a primary energy source? Primary energy source is just a energy source as it's found in nature, whereas a secondary energy source is an energy source that's usable by us. For example, the energy that my camera is using to record this right now is stored electrical potential energy. Well, where that energy can't come from, it came from some natural source. However the electricity was produced, where I charge my battery and when I charge my battery. So are all these taking natural forms of energy to convert into something else? If so, they're all primary energy. Well, wind turbine converts wind energy, natural energy, into electrical potential energy. So that's a primary. Photovoltaic, well, it takes solar radiation. That's a natural form of energy that's not directly usable. And same thing with fossil fuel. You're taking stored chemical energy that is in fossil fuel. So these are all primary energy sources, 1, 2, and 3. The orbital radius of the Earth around the Sun is 1.5 times that of Venus. What is the intensity of solar radiation at the orbital radius of Venus? So there's a solar constant in here in your data booklet in the portion with constants. All right, the solar constant, S, I'll just call it, well, it's 1.36 times 10 to the 3 watts, or 1,360 watts per square meter at Earth. So at Venus, it must be greater than that because Venus is closer. So that immediately gets rid of those two. So we have to be at either 2 kilowatts or 3 kilowatts. We are at I'll just call 1.4 kilowatts. Now, the intensity is going to be proportional to distance squared. So if we square how much farther Earth is from the sun, 1.5 squared is 2.25. So now I'm going to do 1.4 times 2.25 because I want to get a bigger number for where Venus is. So 1.4 times 2.25, well, I know that's going to be bigger than 2, right? So it's going to be 3. So you don't have to, that is something most of you would probably want to use your calculator for, but 1.4 times 2 alone is 2.8. And then another quarter 1.4, quarter 1.4 is going to be a little bit more than 0.3. So it would be actually more than 3 kilowatts, but this is all very, very approximate. So it would have to be D. And that's that. That is paper 1 for the May 2019 version 2 exam.